Okay, so the first thing, divisibility rules. This is not like anything that's you need to be, it's just for your convenience, just to know how can you tell if a big number is divisible by a smaller number. There's some rules that you can quickly use that'll tell you if any number is divisible by 2 or divisible by 3, etc. So obviously any number that's even is divisible by 2, right? The divisibility rule for 3, this is a really important one. You use this one a lot. So how do you know if a number is divisible by 3? All you have to do is add the digits up, and if the sum of the digits is divisible by 3, then the whole number is divisible by 3. So for example, if I have the number 723, if I add the digits up, 7 plus 2 plus 3 equals 12, which is divisible by 3. So the whole number is divisible by 3. One thing that's kind of nice about this is if I had an enormous number, when I added the digits up, if the sum of the digits was still a pretty big number, I could do it again. I could add the digits of that number and just keep going. The divisibility rule for 4 is really simple. All you have to do is look at the last 2 digits of the number, the ones digit and the tens digit, ignore everything else, and if the last 2 digits of the number are divisible by 4, then the whole big number is. Okay? 5 is easy. If the last number is a 0 or a 5, it's divisible by 5. 6 is easy too. It's just a combination of being divisible by 2 and divisible by 3 makes it divisible by 6. So it has to be even, and the sum of the digits has to be divisible by 3. Okay? 7 is a weird one. 7 is a really weird one. Let's look at a quick example of 7. I want to talk you through this one because it's so bizarre. So if we had a number like 3192, how about? Here's how this works. You take the last digit of the number you're testing, you double it and subtract it from the remaining 3 digits. So in this case, I'm going to take the 2 and double it. Whoops, I kind of missed there. We're going to double the 2 and subtract it from 319. And that's going to give us 315. Okay, that still is pretty big, so we'll do it again. If I double the 5 and subtract it from the other 2 digits, I get 21, which obviously is divisible by 7. So you just do this until your final number is, if the final number is either 0 or a number that's divisible by 7, then the big number was divisible by 7. If you don't end up with one of those 2 things, if you end up with a number that's not 0 and not a number divisible by 7, then the original number was not divisible by 7. The divisibility rule for 8 is kind of like the one for 4, only this time you have to take the last 3 digits of the number. So for example, if I had something like, let's see, how about this one? What if I had the number 35,703,408. All I have to do is just look at the last 3-digit part of the number. If that's divisible by 8, which 408 is, then the whole number is divisible by 8. Okay? Divisibility rule for 9 is the same thing as the divisibility rule for 3, only you use 9s instead of 3s. So for example, 729, we'll sum the digits. 7 plus 2 plus 9 equals 18, which is divisible by 9. So the whole number is divisible by 9. And then finally, the divisibility rule for 10, if the last digit's a 0, the whole thing's divisible by 10. Okay, I'll put these in the notes that'll show up in plan book. Okay, the last part, I want to go through 3 examples, and this is for the assignment, the 5.5 assignment. So this is for, all we're doing here is nothing's different. It's all the factoring stuff we worked on in section 3.4, only we're using it to solve equations, right? So we're gonna factor and apply the zero product property to solve polynomial equations. So how about this guy? What do we always do first when we're solving a polynomial equation? Yeah, set it equal to 0, right? We got to put it in standard form. So in this case, we want to make the leading term positive, which it already is on the left side. So we'll just subtract the 48x over to the left side. And that's going to give us 3x to the 5th minus 48x equals 0. Okay, good. First step, always set it equal to 0. Okay, now what? Now we got to factor, right? When we're factoring, what do we always try to do first when we factor? What do we always try to do? It doesn't always work, but we always want to try to do something. Greatest common factor. Yeah, we want to see if we can undistribute a greatest common factor. Okay, can I? Is there a GCF here I could undistribute? Yeah, I could take out a 3x, couldn't I? Okay, what's left behind? Yeah, 3x times what is 3x to the 5th? X to the 4th, right? Minus 3x times 16 is 48x. And that whole thing is equal to 0. Okay, so we're just, at this point, we just have to keep factoring until we can stop, right? We can't stop until each of our factors is at least down to the x squared, to quadratic. It has to be quadratic or smaller. That one is not. That's x to the 4th, this binomial, so we have to keep going. We don't have a choice, right? What can we do? Yeah, now it's a binomial. Think about the strategy here. It's all based on the number of terms in the polynomial. We have a 2-term polynomial factor, the yellow factor. So 2 terms or binomial factor always uses our patterns. We've only got 3 patterns. Difference of squares, difference of cubes, and sum of cubes, right? Sum of squares is not a pattern. So the only one this could fit is difference of squares, right? So let's write that one down. Difference of squares pattern. A squared minus b squared equals what? Good. A minus b times a plus b. And this is like what squared minus what squared? Jordan, this is a difference of squares how? What's being squared in the first term? But what, there you go, x squared squared is x to the 4th, right? So we're going to think of that as x squared squared minus 4 squared. Okay, good. So there's our yellow factor written as a difference of squares. So how is that going to factor? Sam, how's that going to factor? And again, here's our pattern, right? See, so how do I factor that difference of squares, the yellow difference of squares? These are x's? Squared though, right? Because look, my a is an x squared. I get a squared is x squared squared, right? Yes, right? Because that's what's being squared in my difference of squares, right? My a is x squared, okay? Minus, well, you tell me, what's going to happen here then? Minus 4, right? Because 4 is what's being squared. And plus 4. Yeah, there we go, okay? And then out front, we've got that 3x. Okay, now we have an option here. Both of the yellow factors are quadratic. They're down to x squareds. So I don't have to factor anymore, even if I can, but I could choose to if possible. How about this first one? Does that factor any further? So how could I go further with that? Chaz, what could I do there? What pattern's that going to fit? Yeah, good, because that's x squared minus 2 squared, isn't it? Right? Do you guys all get that? Okay, good. So that's 4 we're going to replace with a 2 squared. So that's going to break up into x minus 2 times x plus 2. We've got this 3x that's already done out front. Now, what about the other yellow factor? What about that one? Can I factor that? I can't, because there is no sum of squares pattern, right? So my only choice for this one is I've got to set it equal to 0 and solve that quadratic equation, which is no big deal. We got really good at that in Unit 4. So x squared plus 4 equals 0. How would I solve that? Yeah, I'm just going to isolate the x, aren't I? I can point to a single x, so I can isolate it. So x squared equals minus 4. If I square root both sides, that's going to cancel the squared, isn't it? And so when I square root both sides of an equation, what do I have to include? Plus or minus. And then the square root of negative 4, what's that going to be? 2i, right? Square root of 4 is 2. And the negative inside becomes an I outside, right? So how many, I guess we got 2 solutions there. We got to go back and find the zeros of the other factors though too, right? So what's the value of x that makes x plus 2 equal to 0? Okay, everybody agree? So we get negative 2, x minus 2 is 0 when x is 2. And 3x is 0 when x is 3 times what is 0? 0. There you go. Yeah. And whenever you have a monomial factor like that, some number times the power of x, you're always going to get x equals 0 for the 0 of that, right? So how many should we have gotten for this? 5. How many did we get? Yeah. 1, 2, 3, 4, 5. 1 for the plus, 1 for the minus. Right? Yeah. Yeah, you have to put them all in, and you have to put them all in separately, right? Because so you'd have to break this one into separate them with a comma in Math Excel. Okay, give me 1 to 5. How we doing? Okay, questions? Okay, probably just take some practice. Yeah, no, that's fine. That's fine. So I just want to go through one of every type, so when you do the assignment, you got this fresh in your mind. Okay, so there was one. What was the big deal about that one? Well, we did a lot of binomial stuff, didn't we? Right? We had to use a lot of binomial factoring patterns. And we had to, when we found the zeros, we had one factor where we had to solve a quadratic, right? And we solved just by isolating x, no big deal. Okay, how about this one? So it's already equal to 0, isn't it? How many terms in that polynomial? 3. What's our strategy for a 3-term polynomial? Well, I mean, we could use the quadratic formula, but it's easier if we can to just find magic numbers, isn't it? Right? To factor this, to make it look like something quadratic. But in order to make this look like a quadratic trinomial, right now, would you agree the values of a, b, and c in that trinomial are 1, 3, and negative 10, right? Everybody agree? Okay, we need to make this look, though, like 1 times something squared plus 3 times something minus 10 equals 0. It needs to look quadratic. Like in Unit 4, that would have just been x squared plus 3x minus 10 equals 0. In Unit 5, what is it that we could be, what could the pieces be for this quadratic trinomial? Carter, what's going to go in the parentheses there to make this look quadratic? No. Think about like, I need something squared to turn into p to the 4th. P squared, yeah, there you go, right? So I could make this quadratic in pieces of p squared, right? Now that looks quadratic, doesn't it? It looks like something squared plus 3 times something minus 10. That looks like a unit 4 problem, right? Are there magic numbers so we could factor that trinomial? That multiply to negative 10 and add to 3? 5 and negative 2, right? Okay. So then this would split up into the magic numbers plus 5 and minus 2, but what has to go there and there? P squared, yeah. Instead of just being a plain old x, it's going to be whatever this quadratic was in pieces of, which is p squared. And it has to be that way because if I were to expand this out, this times this needs to give me, first times first needs to give me p squared squared. So it just must be p squared times p squared, right? Okay, so now I've factored it enough to where I don't have to factor, and can I even factor any of those? None of them will factor anyway, will they? Right? Because there is no sum of squares pattern, and 2 is not a square. So what do? Yeah, I just need to find the zeros of those two factors. So to find the zeros of something, I just set it equal to 0 and solve. So the first one then just gives me the equation p squared plus 5 equals 0. That's easy to solve. What are the 2 steps to solve that one? Elise, what do I do to isolate the p there? Because that's all I have to do, right? What do I have to do to solve that, to isolate the p? Subtract 5. Now what? Does that make sense? Because I got to get the p by itself, so I have to undo the square, don't I? So I'll square root each side, right? And the square root is going to cancel the squared. So we're going to get p equals, if I square root both sides of an equation, what do I have to include? Plus or minus, good. So I've got my plus or minus sitting out there. Oh, I didn't want to do that. What happened there? Oh my goodness. There we go. Scroll down. There we go. Okay. So equals p equals plus or minus 5i. Good. Because I've got the square root of negative 5. So that's going to give me 5i. So there are 2 solutions. How many should I get total? 4, because it's a 4th degree polynomial equation, right? How about the other 2? Let's look at these guys. What am I going to do there? Add 2 in square root, so I'm just solving the equation p squared minus 2 equals 0. So p squared equals 2. Square root each side. If I square root both sides, what do I have to include? Plus or minus, right? Okay, now giving you a chance to and square root of 2, can that be simplified? No. So I'm just stuck with plus or minus square root of 2, and there's all 4 of my solutions. 2, 4. Give me 1 to 5. Okay, we know how many because when my original polynomial, the degree is 4. So that means we're guaranteed to get 4 complex solutions. Now, if I had a multiplicity bigger than 1, it would count for more than one solution, but I haven't had any like that today. Like if I had, for example, if I had an x squared factor out front, I don't think we've had any. If I had like an x squared factor, like x squared equals 0 when x equals 0, so there's a solution, but it counts as 2 because the x was squared. See what I'm saying? Okay. All right. I'm done. You guys can work. 5.5. What's that? I think so.